Over the last few videos we've looked at the equation for a straight line. In this video I'd like to show an example of why it can be incredibly useful to have a line represented as an equation. So given two lines in the form y equals mx plus c, we're going to see how we can find the intersection point between these two lines. That's the point in 2D space where these lines cross. Now this is just one example of many mathematical theories which can utilize the equation of a line. Being able to determine the intersection point between two lines actually has countless uses in computer graphics and programming. Whether we're clipping polygons to a 2D screen, for example, or perhaps trying to predict collisions between objects moving in 2D, there are many different problems that might arise in which the theory covered in this video, or theories that derive from it, may be useful to us. But more important than the direct practical application of this theory is the demonstration of why having something in a mathematical form can allow us to determine generic solutions to problems. And by having a generic solution, it allows us to write a computer algorithm to solve that problem. And of course, if we're working as programmers or we're working in computer graphics, it's going to be very useful to us if we can solve problems with computer algorithms. So starting out, hopefully we can see quite clearly that two infinitely long straight lines are going to intersect at just one single point as long as they aren't parallel to each other, so as long as the gradient of both lines is not the same. So let's take a look at that right now. If I was to draw a line on our whiteboard, and then I was to draw any other line, even if it was almost similar but had just a very slightly different gradient, you're going to notice if they're infinitely long, even if they weren't to cross on our whiteboard, eventually as they went off into space they would cross. And we can see that two lines, no matter how they cross, always cross at a single point. So the only time when two lines are not going to cross is if their gradient is the same. If they have the exact same gradient, no matter how they're positioned, they're simply never going to cross. They're always going to travel in the same direction, and that means they're never going to be getting closer to each other in either direction, and that means they're never going to cross. But as long as they're not parallel to one another, two infinitely long straight lines will always intersect, and they're always going to intersect at a single point. So let me just draw a line that does actually intersect this. Fantastic. And then grab my whiteboard so that I can draw on it. So we know that the equation for a line, that equation is y equals mx plus c. That equation for a line is going to give us a y coordinate for every x coordinate that we put into the equation. And that's going to give us a series of points on the line. So if we took this line, for example, as we're entering x coordinates, we're going to get a series of y coordinates. And that's going to give us a series of points along this line. As I undo that. Similarly, on our other line equation is also going to give us a series of points on the line. We enter x coordinates, it gives us a corresponding y coordinate, and that's going to give us points along the other line. So the point of intersection, this point right here where the two lines cross, is going to be the point in which on both lines we have the same coordinates. So there's only a single point where we can enter a single value of x into the equation for both lines and we'll get the same value in y for both lines. So if we had two line equations, and I'm going to use the general form of the line equations here. So if we had two line equations, the equation of our first line is y1 is equal to m1 x1 plus c1. So it's just our y equals mx plus c, but everything is subscript 1 to indicate that this refers to our first line. And if our second line was the equivalent, so y2 is equal to m2 x2 plus c2. So again, it's just y equals mx plus c, but being a different line, it's going to have a different m and a different c. Well, we know that the point of intersection is going to satisfy both equations. So if we said that point where these two lines cross right here, that point has the coordinates xi, yi, I being a way of indicating intersection in this case. So we have a point of intersection, xi, yi, well, we know that this point satisfies both equation 1 and equation 2. So that means I can rewrite both of these equations. I can say, well, if I know that putting xi into equation 1 is going to give us yi, then I can rewrite this as yi is equal to m1 xi plus c1. And if I know that putting xi into equation 2 is going to give us yi, then I can rewrite equation 2 as yi is equal to m2 xi plus c2. So let's scroll down a bit. So we've now got these two equations, and what do we notice? We have two things that are equal to yi. That means if this is equal to yi, and this is equal to yi, then this part of the equation must also equal this equation, because they both equal the same value. That means we can put the two equations equal to one another, which allows me to write the following. m1 xi plus c1 is equal to m2 xi plus c2. So let's have a look at what we have in this equation. We have a constant value m1, a constant value c1, a constant value m2, a constant value c2. So all of these are going to just be numbers. When we're dealing with actual lines that are intersecting, these are all constant numbers, and we have a single variable xi, and it's the same variable in both cases. So this should mean that we can rearrange this equation to solve for xi. We can get xi in terms of m1, c1, m2, and c2, and that will allow us to determine, based on the gradients and the intercepts of both of our lines, the x-coordinate of our point of intersection. And as long as we can find the x-coordinate, we can then take that and we can use either of these two equations here to determine the y-coordinate of the point of intersection. So let's rearrange this equation and solve for xi. It's going to be pretty simple. The first thing I'm going to do is I'm going to bring c1 over to our other side. To do that, I need to cancel an addition, so I'm going to subtract c1 from both sides. So m1 xi is equal to m2 xi plus c2 minus c1. The next thing I'd like to do is bring our xi term over with our other xi term, but I can't separate m2 and xi just yet, because if I was to divide by m2, I'd be dividing everything by m2. So what I'm going to do is I'm going to bring this entire term over. I'm going to subtract m2 xi so that it moves over to this side. So I'm going to have m1 xi minus m2 xi is equal to c2 minus c1. Now we can use our distributive law to basically bring xi out of both of these two multiplications, so that we have xi, open parentheses, m1. Now because we're subtracting here, we must make sure that we subtract inside the parentheses, minus m2. So you can notice if we were to expand this, just to check, xi times m1 gives us m1 xi minus xi, excuse me, xi m2 gives us m2 xi. So that is equal to c2 minus c1. And finally, we want to get xi on its own, so I'm going to cancel the multiplication that's here by dividing both sides by m1 minus m2. So finally, we know that xi is equal to c2 minus c1. We don't need parentheses, but I'm going to use them just for clarification, divided by m1 minus m2. So this is an equation that we can put four constant values in, the intercepts and the gradients for both of our lines, and that will give us the x-coordinate of the point of intersection. Once we have that x-coordinate, we can plug that back in to either of these two equations, basically to either of the equations of either line, because as we said, the point of intersection is the point that when we put an x-coordinate into both lines, we get the same y-coordinate back. So we could use either line equation to get the y point of intersection. Now we do need to be careful here and notice that we could get a divide by 0. And notice the case where we get a divide by 0 is if m1 is equal to m2, because in the case that m1 is equal to m2, then that means that m1 minus m2 is going to be 0, and if we're dividing by 0, we've already discussed, that's very bad. Things are going to explode. But, of course, if the case was that we were dividing by 0, if the case was that m1 is the same as m2, then that means the gradient of both lines is the same, and that means they're either parallel or they are the same line. And because of that, we saw earlier when we were drawing lines on the board, if they're parallel, they're never going to intersect. So this equation is still holding true. If the two lines are parallel, we get a divide by 0, we can't divide by 0, so that, in effect, is telling us there is no point of intersection. Our formula breaks down. Of course, if you're programming a line intersection algorithm utilizing this formula, please be sure to check that the gradients are not equal to each other before you evaluate this formula, because otherwise, if they are equal, you're going to get another one of those nasty divide by zeros. So okay, as I said, once we've found xy, we can put xi into either of these two equations to find our value of yi, and that's everything we need to find our point of intersection. We've found xi, we plug that into one of the equations, that gives us yi, which gives us our point of intersection. So let's test this on a simple example. So I'm running out of whiteboard space, so I think the best thing for us to do is to bring up a brand new layer. And I'm going to use the example where we have one line that is y is equal to 4x plus 6, and the other line is y is equal to 3x minus 2. So what do we know about this? Well, if I was to say that this is line 1 and this is line 2, then we could say that, okay, we have m1 equal to 4, because the gradient of our first line is 4. C1 is equal to 6, because that's the intercept of our first line. M2 is equal to 3, the gradient of our second line. And C2 is equal to minus 2. We now have the four constant values that we need to evaluate our xi equation. So xi is equal to, if you recall back, it's equal to C2 minus C1 over m1 minus m2. So we can now plug numbers into this equation. So xi is going to be equal to C2 is minus 2, minus C1 is 6, over m1 is 4, minus m2 is 3. So we can now calculate this. Xi is equal to minus 2 minus 6 is going to give us minus 8. 4 minus 3 is going to give us 1, so obviously this is minus 8. So the x-coordinate of the point of intersection between these two lines is minus 8. We can now take this and use it in either of these equations to calculate the y point of intersection. So I'm going to use our first equation. So y is equal to 4x plus 6, which means yi is equal to 4xi plus 6, which is equal to 4 times minus 8 plus 6, which is equal to minus 32 plus 6, which is equal to minus 26. So our point of intersection, xi, yi, is equal to minus 8 minus 26. And we can actually check this by using our other line equation, because we know for the point of intersection, the same x-coordinate, that x-coordinate of minus 8, should give us the same y-coordinate. So let's check that. Y is equal to 3x minus 2. So yi is going to be equal to 3xi minus 2, which is equal to 3 minus 8 minus 2, which is equal to minus 24 minus 2, which again is equal to minus 26. So both of these equations, given the point with xi equal to minus 8, are both giving us yi equal to minus 26, which means this is the point in which both of those lines intersect. So now that we've seen our formula, and I will just to recap show that, so that's right here. Now that we've seen this formula, I'd like you to use that formula to find the point of intersection between a number of lines. So the first question that I'd like you to answer is to find the point of intersection between the following two lines. So the lines are y is equal to 3x plus 4 and y is equal to minus x plus 2. So go ahead and give this a try, find the point of intersection using our equation, and then once you have an answer or if you get stuck, unpause the video and I will work through the solution on the whiteboard. Okay, welcome back everyone. So if you recall our equation to find xi, that's equal to c2 minus c1 divided by m1 minus m2. So we can plug numbers into this now. So it's equal to c2 is 2 minus c1 is 4 divided by m1 is 3 minus m2 is minus 1, so minus 1, which becomes 2 minus 4 over 3 plus 1. Well, 2 minus 4 is minus 2. 3 plus 1 is 4, so it's equal to minus 2 over 4, which is equal to minus a half. So our point of intersection has an x-coordinate of minus a half. We can now take this and plug it back into either equation. So I'm going to plug it into, I don't know, let's plug it into this equation. Might be more simple to find the answer. So y is equal to minus x plus 2. Therefore yi is going to be equal to minus xi plus 2, which is equal to minus a half plus 2, which is equal to a half plus 2, which is equal to 2.5. So our y coordinate of the point of intersection should be 2.5. To check that, we of course can use our other equation, well that's the one we first used, so we can use our other equation. So y is equal to 3x plus 4. That means that yi is equal to 3xi plus 4. That's equal to 3 times minus a half plus 4, which is equal to, well, 3 times minus a half is going to be minus 1.5 plus 4, which also equals 2.5. So indeed it is giving us the same answer, which means that the point of intersection for those two lines is minus a half in x and 2.5 in y. So that's question 1. Let's move on to another question. So I'm going to bring up a new layer. Fantastic. So question 2, again, I'd like you to use the equation to find the intersection point between two lines. In this case, the two lines are y is equal to minus 4x minus 4, and the second line is y is equal to 4x plus 8. So go ahead and pause the video, give this an attempt, and when we come back, I am going to work through the solution on the whiteboard. Okay, welcome back everyone. So again, we know our equation for xi is equal to c2 minus c1 over m1 minus m2. So that's going to be equal to c2 is 8 minus c1 is minus 4, so 8 minus 4 over m1 is minus 4 minus m2 is 4. So we can now work that through. So that's equal to 8 plus 4 over minus 4 minus 4, which is equal to 12 over minus 8. which is equal to minus 3.5. So that's, wow, there's me thinking in fractions and talking in numbers. That's actually equal to minus 3 over 2, which is equal to minus 1.5, not minus 3.5, which is me thinking in fractions and then speaking out loud. My apologies for that. So again, 12 over minus 8 is going to be equal to minus 3 over 2, which is equal to minus 1.5. So that's our x-coordinate, minus 1.5. Let's find our y-coordinate, and we can use either of these equations. In this case, I'm going to check with use our first equation to find the answer and check with our second equation. So y is equal to minus 4x minus 4. So y is equal to minus 4x minus 4. So that's equal to minus 4 minus 1.5 minus 4. Well, that's going to be equal to positive 6 minus 4, which is equal to 2. So our y-coordinate should be 2. Let's check that with our second equation. Y is equal to 4x plus 8. So y is equal to 4x plus 8. If we use our x intersection point coordinate 4x, we're going to get y is equal to 4 minus 1.5 plus 8. 4 times minus 1.5 is going to be negative 6 plus 8, which again is equal to 2. So that is indeed the correct answer. So the intersection point between these two lines is the point minus 1.5 and 2 in y. So I'd like to set just one last question before I wrap this video up. So bring up a new whiteboard layer, and question 3. Again, I'd like you to find the intersection point between two lines, and the two lines I'd like you to find the intersection point between are 3y is equal to 3x plus 9 and y is equal to 3x plus 9. So go ahead and pause the video, attempt this question. When you come back, I'm going to work through the solution. Okay, welcome back everyone. So this is a little bit of a trick question, because if you were just glancing here, you might think that these two equations give us the same gradient and the same intercept. And of course, if we thought we had the same gradient, that would mean we would not have a point of intersection. However, you need to be careful, because we need our equation to be in the form y is equal to mx plus c. And here we have 3y. So in order to get this first equation in the form y is equal to mx plus c, we're going to have to divide that equation by 3. So if we were to divide our first equation by 3, we'd get y is equal to, because 3y over 3 is y, 3x over 3 is x, plus 9 over 3 is 3. So really the two equations that we're finding the intersection point between is y is equal to 3x plus 9 and y is equal to x plus 3. So now that we know that, we can solve for the point of intersection. Now I'm going to say that this is our second equation, which means that m2 is equal to 3 and c2 is equal to 9, and that this is our first equation. So m1 rather is equal to 1 and c1 is equal to 3. If we plug that into our equation for xi is equal to c2 minus c1 divided by m1 minus m2. We can plug those numbers in, so it's equal to c2 is 9 minus c1 is 3 divided by m1 is 1 minus m2 is 3. So that's equal to 6 over minus 2, which is equal to minus 3. So that's xi is minus 3. Let's find yi. We can put that into either equation. I'm going to put that into our equation y is equal to x plus 3, which means that yi is equal to xi plus 3, which is equal to minus 3 plus 3, which is equal to 0. And just to check that indeed the y coordinate is 0, let us use our other equation. So let's use our y is equal to 3x plus 9. So that should mean that yi is equal to 3xi plus 9, which is going to be equal to 3 minus 3 plus 9, which is equal to minus 9 plus 9, which is indeed also equal to 0. So that is the correct answer. So again, the intersection point between these two lines is the point minus 3 in x and 0 in y. So there really is nothing to it. Having our lines represented as mathematical equations made it incredibly easy for us to solve for the intersection point in a general way, in a way that works for any combination of lines. And once we've found that formula, we can now use it time and time again to solve for any lines, which is perfect for us because it allows us to write this as a computer algorithm, and then no matter what the lines in our program are doing, we can take those, we can enter it into the algorithm, and we can work out if there's points of intersection. Now, as noted earlier, this is only going to work when the lines intersect. If the gradient of both lines is the same, we're going to get a divide by 0, and also we're going to obviously, in terms of line theory, they're never going to intersect because they're parallel. So if you're programming this, you just need to check to make sure those two gradients aren't equal before you evaluate this, because if they are equal, the lines are parallel, we don't get an intersection, and if you were to evaluate this equation, we would get a divide by 0, which obviously is bad. But that's all there is to it, this tiny little equation, very, very simple. And with that, that is going to conclude this video. Thanks a lot, everyone.